Thank you. So I think it's a very good transition that Professor Porrage is giving me, since he gave, in a way, a very nice overview of how our generation of wireless communication evolved. And as you know, as we are living during this 5G era, research-wise, actually we are already working on trying to look at beyond 5G and 6G. And often in our community, as you know, we are after Olympic records. How can we go for higher data rates? How can we lower the latency, increase the reliability? How can we make the connectivity more massive in terms of connected IoT device per meter square? But we tend to forget that we still have an important digital divide. According to the latest ITU reports, we still have about 1/3 of world population, 3 billion people, unconnected. The reasons are many. I will talk about that as we progress in the talk. And there should be effort to, in my opinion, try to address this issue, an issue that I would not say has been neglected, but essentially from a business perspective, from a, let's say, financial and profit perspective, was hard to achieve as part of the 1G to 5G. And a few of us, when we started looking at beyond 5G and 6G, we felt that there is maybe an opportunity to take advantage of this new generation of communication system to push some of the United Nations SDGs and in part touch upon this digital inclusiveness, or trying to bridge the digital divide to bring equality of access to users across the globe. Of course, there are other important aspects that need to be addressed as we go toward beyond 5G in terms of energy efficiencies and EMF radiations and security and privacy, but I'll be focusing mostly on the basically aspect of digital inclusion. And by the way, when someone works on this topic, indirectly you are working on very related topics such as communication in post-disaster or emergency communication, because we tend to forget, those of us who are working in very well or living in very well connected environment, that because of a disaster, because of an earthquake or flood, that connectivity can be lost, and you have to deal overnight with the problem of connecting the unconnected. You have kind of these events with a super high capacity over a very short period of time, and people tend to be unconnected or disconnect because of the surge capacity, and you need to solve that problem. You are sending, let's say, scientists in the middle of nowhere, and you would like to get streaming from this remote location in the Amazon or Antarctica. In a way, it falls under that umbrella, and it goes without saying that military missions often happen in such kind of environment. And of course, the focus is on connecting people, but indirectly, once you connect people, or once you bring that umbrella, you are also going to be able to connect all kinds of machines, IoT device, and enable a lot of interesting applications in the context of environment monitoring, smart agriculture, and so on. So that's a little bit kind of a motivation why there is an interest in working in this area. So as an example here, and just to give you a taste on the kind of work we have been doing, is, a lot of the work has been so far mostly on the performance analysis and based on stochastic geometry-based, basically methodologies. So you assume here, for instance, that you have a disaster, and the cellular network that used to be operational and covering this area has been destroyed, and you are trying to bring connectivity. Just to allow first responders and people who are still in this area to communicate. So one way to do that is by sending drones. And the idea was that what altitude these drones have to operate, how many should you send. And, what you can show is that if the disaster radius is relatively small, then actually you can live with a certain number of drones. And obviously, you don't want to have too many drones in a very short or in a very small zone, because they start interfering with each other, assuming that they're using the same spectrum resources. So it's always a nice sweet spot in terms of the optimal number of drones that you need to pick for a particular disaster radius. But what we also realize that when the disaster radius becomes too big, then it doesn't make any sense to send a swarm of drones. Actually, what makes sense is to go high in altitude and send a high altitude platform station. Why am I putting this slide up front? Because that's one of the concepts or one of the ideas that I would like to convey. It's a little bit marginal now as far as research is being done in our community, but it's one of the topics I feel strongly about in terms of a nice complementary solution to all the interesting work that's done in satellite communication. So what I'm trying to say here, when disaster radius increases a certain radius, there is no point to send many drones, like 40 or 50 drones. 1 or 2 hubs is good enough to cover these areas. And we'll go back to this concept of hubs as we progress. So now let's go back to this digital divide problem and try to understand one of the main issues behind this digital divide. It's called or known as a backhaul challenge. So if you look at this diagram showing the quality of experience, you can measure it in terms of data rate, in terms of delay, and so on, as function of the cost per user, and here we're focusing in remote, low population density area. So we all know that fiber optics was kind of what made connectivity good in urban environment. Fiber optics work very well in highly dense environment. Now, it doesn't make much business sense to dig and lay hundreds, if not thousands of kilometers to reach these hard-to-reach low-density population areas. And that's why, optical fiber doesn't work when you want to reduce the cost per user. Now, classical satellite systems have been essentially designed for broadcast type of operation. Professor Porrage can remind us that actually from budgeting perspective, when you talk about geosatellite, that's not the way you want to use it for internet browsing. So the holy grail, what we're trying to achieve here in all this kind of research, is how can we get good quality of service for data, multimedia type of transmission at a low cost per user, even in remote, low-density population areas. And that's kind of what we are trying to achieve. And if you read this statement made by Tesla 100 years ago, you can see that Tesla was already thinking in a pretty much 5G, 6G terms already at that time. So how can this be achieved? Actually, the concept is very simple. It's really completely opposite the way we design a cellular system in a highly dense populated environment. So instead of aggressively reusing the spectrum and going for the small cell, actually what you need to do is to go for bigger and bigger cell with the same piece of equipment and get the maximum coverage. How can you achieve that? One of the very simple way is just to reuse some of the existing TV tower and attach to them base stations, and then try to capitalize on the low part of the spectrum, VHF, UHF, with good propagation kind of reach, to be able to cover with a single base station few tens of kilometers. Actually, we did a very simple analysis using a data set from the ITU in one province in Ethiopia, where essentially there is a big digital divide concerns. And what we showed in this study is that essentially, if you look here, here, these are population density maps or data that you can get, for example, from Facebook. That's blue, highly dense population area. As you go into yellow, it's a low density population areas. You see where the base stations are placed in red. And here are TV towers. So our study was about, what about if we equip this TV tower with massive MIMO technology, and actually even if we are able to afford and to move one of these stations in order to optimize the coverage, what we showed that just by doing that, you can basically gain roughly 20% in terms of coverage or in terms of connecting more people. Now, let's assume you don't have access to these TV towers that tend to be often on the top of mountains or hills. How can you get this gain in altitude or in height? One way is to use this so-called tether balloon or tether blimp. Few companies in the US are using this in rural America, and essentially what you do, you take a tether blimp, which kind of capitalize on the concept of buoyancy, so it's filled with basically gas that is lighter than air, let's say helium, to stay aloft, and you have this cable that gives power and gives data backhaul, and then you attach a base station to that blimp, and you are getting few tens of kilometers of radius of coverage. Now, The next step is to go even higher. And here comes again the concept of hubs. So hubs stand for High Altitude Platform Station. Some people like to call them High Altitude Pseudo-Satellites. So these are platforms that can come in different forms. They can come in the form of gliders or fixed-wing big drones, airships or basically blimps, again filled with, for example, helium, or balloons. And they are operating in the stratosphere, something like 20-kilometer altitude. So just for calibration purpose, the airplane that we use to travel flies roughly at 10 kilometers. So it's at twice the altitude of airplanes. Now, once you use these hubs and you attach a base station to them, you can have, tens of kilometers, few hundred of kilometers of coverage with a single base station. So actually, hubs is a very nice, I would say, trade-off between ground base station that we know very well how to design, how to operate, satellite, and there is a big, of course, race towards space where we know about what's going on with the Starlink and Kuiper and OneWeb. So hubs in between can be called the near space, basically communication network. They can help basically people in urban area by giving some offloading capabilities when needed. They can help people in suburban area with medium population density, and they can even serve very low population density area in rural areas. However, I think they are still complementing satellite connectivity that has essentially a very interesting strength in terms of deep rural or maritime environment. So hubs is in between, and if you are able to basically build these reliable platforms, I think there is a lot of potential for connectivity from the stratosphere or from the near space. So one experiment was conducted not very far from our university in the Red Sea in collaboration with Deutsche Telekom and the Stratospheric platform. So we're basically trying to demonstrate the capability of 5G or the possibility of having a 5G connectivity with the hubs, and that was a successful experiment. And here, going back to the remark made by Professor Porrage just before me, I think one of the main reasons behind the failure of the Teledesic and Globestar at the time, of the late 90s, is because they all require different kind of phones. And basically the economy of scale didn't work out, so you had the phone that you have to use when you were trying to talk to Globestar or another part of the world, Thuraya type of communication. And when you are in an urban environment, you have to go back to 3G or 4G phones. The beauty of the hubs is that the same phone that you are using for your daily life to communicate within an urban environment can be reused in a deep rural or in maritime environment. And that was the purpose of this experiment. So if you look at this experiment, it was over a few, kilometers, and what we have shown here is at some point, so in blue, that's the distance between the base station, let's say, and the radius of the coverage. As you see, the blue is relying on, is showing downlink throughput or spectral efficiency, and in blue what we are seeing here is a data rate that we can provide using a kind of terrestrial base station, which at some point, of course, is going to go down, whereas from hubs, you maintain pretty much over the whole coverage area a constant throughput and a constant spectral efficiency. And that demonstrates in a way that essentially you can maintain coverage over long distance. That was just obviously a first trial, and a lot has to be done in order to demonstrate the feasibility and the endurance of these kind of networks. So one of the kind of studies that we have conducted was to try to kind of understand the importance of hubs in the context of integrated ground-air space network. And what we have shown is that when you use hubs as relays for satellite communication, they can actually greatly improve the coverage probability. So here actually, as mentioned earlier, if you put a high expectation from satellites, essentially it doesn't work. You just cannot have a coverage area. The budget link is very bad for satellites, so you need the help of hubs as relays. And actually, if you compare here, an increase in the number of hubs compared to an increased number of satellite is more advantageous for the increase in satellite in terms of gain, in terms of coverage probability. So if you want to increase the number of satellite, it's more beneficial to increase the number of hubs compared to increase the number of satellite if you want to increase your coverage probability. So I thought it was a 30-minute talk, so I will go a little bit fast about these slides. They will be available for you for completeness and reference value. But one important thing when you design hubs, basically a based network, is that hubs are either, for now at least, they are either solar-powered or hydrogen-fueled. And if you are using solar-powered hubs, they will have to operate at different altitude between day and night. Why? Because during the day they will tend to go up in order to be more exposed to sun and collect as much solar power as possible. And in that case, your system design will be targeting, let's say, maximum sun rate operation. And then, of course, during the day, you will be kind of trying to charge your battery. As the day progresses and you go towards the night, the hubs will tend to go to lower altitude in order to save in terms of potential energy. And in that case, you will not target a maximum spectral efficiency or sun rate. Rather, you'll try to minimize your proportional power and you'll tend to use more an energy efficient type of communication methodologies. So that was a study that was done in one recent paper, and based on that we got a few results. But before concluding, I would like to highlight another interesting technology that complement very well hubs, and that again is often neglected in the general discussion about beyond 5G and 6G. And what I would like to highlight is the import of free space optics in this context, in the context of non-terrestrial network, and in particular in the context of hubs communication. Now, why free space optics, which is a technology that's quite mature? It struggled quite a bit to make a name for itself for basically terrestrial application, in particular because of the perception of unreliability due to the fact that it is very sensitive to weather condition as well as to pointing errors. But when you start talking about non-terrestrial network, and when I say non-terrestrial network, hubs and satellites, essentially there are very important factors. Number one is the coexistence from a spectrum perspective between satellite or hubs, or in other words, non-terrestrial network and terrestrial network. That's a very competitive part of the spectrum. Everyone wants to take that piece of the spectrum. Free space optic can bypass that whole problem because you'll be operating on the optical band. Number two, and in my opinion that's the most important argument, is the so-called swap advantage. So swap in the aerospace engineering jargon stands for size, weight, and power constraint. There is no way you can beat optical when you want to transmit at high data rate for basically in terms of size, weight, and power. In other words, if you want to achieve the same kind of capabilities, you will have to go to more massive, bigger antennas, much more weight, much more size. Whereas with very focused laser and full detector, you can achieve that kind of performance. So these two arguments make this paradigm. The paradigm, I think, is one of the paradigms that can allow us to connect a lot of the unconnected people. So this paradigm here is shown in the context of satellite communication, but it can be used exactly the same way with hubs replacing satellite. So the idea is you are having two sides here. One side is what we call the user side. This is a classical beam hopping that is already used in very high throughput satellites, which means by that these are beams that are moving around. They are not static. They go where traffic is needed in real time, depending on how traffic evolves between day and night. Now, obviously, a satellite or a hub is acting as a relay, because at the end of the day, you want to connect all of these users here to the internet. And now currently, this is done in the RF band and the Ka band, a band that is quite saturated. Some of it is going to go as part of beyond 5G and 6G to the user link, and some of it may go to essentially cellular communication. And here is the space that can be filled by free space optic. The idea is to use essentially a free space optic link to connect a hubs or a satellite to the ground. And with that, of course, comes the notion of hybrid. Hybrid because you have an RF side an optical side, a very high throughput because we are talking about terabit per second base station in the sky or in the space. And of course you need side diversity because when you talk about free space optics, of course, you may be affected by weather condition, fog, cloud, and so on, which means you need to have few optical gateways on the ground, so in case the signal is blocked somewhere, you can pick it somewhere else. So this paradigm is a paradigm that we are pursuing, and we are looking at a different aspect of this problem, including an experimental aspect. But let me open here a parenthesis. So some of the studies we do here is performance analysis, obviously, and in particular here we are trying to look at the, kind of out probability, beta rate, capacity of FSO link when you go from the ground to the space, and you get these special functions that are function of, system parameter. Alpha and beta here are the gamma-gamma distribution parameter. Those of you who are familiar with this distribution in radar context, you have parameter due to the pointing error. So here one of the interesting studies that we are able to show is that the pointing error can be modeled by a whole distribution. So, as I mentioned to you, it's very important to model essentially the degree of accuracy. And when you have a drone or a HAPS, obviously there are vibrations. And what you can show is that this pointing can be modeled as a Gaussian, in the X domain, Y domain, and even actually Z domain, if you assume that there is vibration also in the third dimension. All of this, we were able to, in this paper that is being published, show that it can be modeled by a whole distribution, which is generalization of the Rayleigh when the two Gaussian are not essentially necessarily having the same values. Okay. Now, when you put all this together, you get this. I see it as nice, but I know talking to this community, maybe you don't see it as nice as the way I see it. And here I would like to kind of mention this very interesting paper written by Yorgos and Zheng Dao 20 years ago, probably 2003. That's one of the most popular papers in the Communication Society. Until now, it received probably a very good number of citations. Why? Because every time you fail to do all these kind of analysis, or actually, if you don't want to have this complicated formula, you can go to that paper, where basically that paper gives you a very nice methodology to get right away two important metrics that we use to characterize the performance fading channels, the coding gain and the diversity gain. So you may want to get this closed form expression, but at the end of the day, at high SNR, what matters is the coding gain and the diversity gain. And this paper is a beautiful paper that gives you a generic methodology to derive that. And we use it, me and my students, many times in many papers. So now using this, you can do it also for other kind of turbulence. Here we assume log normal turbulence. But I would like to highlight what are the important results you can get out of these studies. So here is the arch probability. We're assuming here an FSO link connecting the ground to a HAPS at 20 kilometer altitude. And you have a free space optic link between the ground and this HAPS. And you are looking at how turbulence can affect the performance of this link. So we have here the arch probability as from the altitude. We have a downlink, an uplink, and the horizontal link. So a horizontal link is two HAPS talking to each other. So what do we notice? We notice that obviously the uplink is performing worse than the downlink. And that's actually understandable. When you look at the atmospheric turbulence profile, it tends to be much stronger towards the lower layer of the atmosphere and goes basically, in terms of intensity, lower and lower as you go up. So when you send an optical beam down to up, you start having the so-called beam wandering and these kind of effect that affect the beam propagation right away from basically the go as you go up. And that's why the uplink tends to be more affected by atmospheric turbulence than the downlink. Now, we also looked at how adaptive optics, the AO here stands for adaptive optics. That's one methodology used essentially for imaging, but has been recycled to be used in the context of communication to reduce the strength of the atmospheric turbulence. And when you use adaptive optics, you get a certain gain in performance. And now, as a final, I think, interesting final remark, and that's well known, but we quantify it here because we take into account pointing error, atmospheric turbulence, variation, the field of arrival of the incoming waves. What we notice is that basically for horizontal link, above 18 kilometers, basically in the stratosphere, the arch probability is essentially zero, which means that you are basically operating in atmospheric turbulence-free environment, which is known, and that's why free space optics is, I think, a very good technology for inter-satellite, but also inter-HAPS, essentially, communication. So, one final slide, and I will conclude. So, as I mentioned, HAPS can be also used as relay for satellites. So the question that we address in this paper was to try to see what will be the optimal location of this relay. So intuitively, you may think that that's where you put your HAPS. Actually, what we show, first of all, that a HAPS can always help. So if you look here, the direct link, which is the link without any relay, gives this kind of ouch probability. As soon as you introduce relay, you are heading again. And then where should you put the relay? It turns out that the optimal location is when this elevation angle is 0, where basically you are exactly on the top of your optical gateway station. And the reason is the same as before. If you are operating in a relatively strong atmospheric turbulence environment, you want to minimize the distance over which you are propagating in this turbulent environment. And this will happen only when this HAPS is exactly on the top of your optical gateway station. So with that, I would like to thank you, and I would like also to highlight again that beyond the fact that we want to go to more speed, lower latency, more connectivity in terms of IoT devices, we want also to help connect more the unconnected, and I believe air and space network, in particular HAPS, which we talk less about, we talk more about satellite, and free space optic, a technology that is mature, but struggled, let's be honest about it, for a ground application may flourish for this emerging non-terrestrial network application. With that, I would like to thank you, and I will be happy to take some questions.
Me again. Thank you. Nice talk. I was wondering, 10, 15 years ago, there was a lot of interest in apps from Facebook and Google, Zoom, balloons and so on. Now, these ideas have a way of coming and reappearing and so on. So I was wondering, because these things didn't pan out then. So now, how is the situation? What's different, or what,
I understand the question.
What's driving this now?
I think, to be honest, because I get this question often when I talk about HAPS, we are not many active in HAPS. There's a lot of work in satellites, so we get these kind of remarks. In my opinion, Loon from Google, Aquila from Facebook were not a failure. They were not a failure from a communication perspective. Actually, they were able to communicate with HAPS, and actually really demonstrated that ourselves with a 5G connection. The problem is how to build a reliable platform in the sky. And I don't think Google and Facebook are the company to do that. When you look at the ecosystem now, aerospace companies are building these aircraft. We are talking about Airbus, Thales, plus some small startup like the one we collaborate with, Stratospheric Platform, which is based in Cambridge, or Sky Dweller. This is actually a project started in EPFL 15 years ago, this kind of solar airplane that went around the globe. These are companies that are not looking at the problem from a communication perspective. They are looking how I can build a reliable, long endurance platform operating in the stratosphere. Once that platform is there, once you have your tower at 20 kilometer altitude, you unlock the potential of the stratosphere. And that's not only communication. You have a payload of 20, 30 kg, plus the right amount of power. You can put a camera, you can put a radar, you can put all kind of sensors, and you can put a base station. And with that, you can do everything a satellite can do, but much better. Because you are much closer to the ground. The budgeting is better, resolution of camera is going to be better. That's why the challenge is, when are we going to get this reliable, long endurance aircraft? My hope, they are going to be there soon. And once they are there, we can do everything I was talking about.
Thank you.
Yeah, was.
Great talk, as always, and we're glad you're back.
Thank you.
It's interesting to go back to this discussion you were having, because just last month, this May, so right before ICAST, I visited NICT. Have you been there?
Yes.
In Japan.
I know them very well.
So They have a big program.
Yeah. I know Dr. Morio Toyoshima.
Yeah.
Yes. And they are looking also at free space optics, and they're looking at hubs. There are, as I said, very few groups, DLR in Germany, NICT in Japan. Most people are doing satellites, very few are doing hubs, but I do believe when we have that platform, we're going to unlock the potential of the near space or the stratosphere. Yes, Polar.
Great talk. This whole link air to ground, I'm sure you have a solution, but precipitation is an issue, right?
Precipitation.
Clouds or snow.
Yes, so FSO is sensitive to weather conditions. But to be honest, again, also, a lot of it is perception. Why? Because when this technology started, it was done more by, I will not call amateur, but there was no the massive scale that is available in the RF. So in other words, the technology has not been perfected, has not been kind of put in a very stress environment that essentially can be competing with RF in a fairground. So it is affected by haze, by fog, by cloud, if you're looking at ground to space, and by heavy rain, not light rain. But the technology is much more mature now than it used to be 10, 15 years ago. So actually we bought few equipment. I have a lab, finally, I was mostly theoretical person, but recently the university wants us to do more experimental work. And we bought some of I don't want to make an advertisement here, but it's a fact. So Google has a startup called Tara. I don't know if you know them. And they really have a very reliable project. And their product, sorry. So we use them to connect some of the islands. So it's always a challenge to connect islands because a submarine cable costs a lot of money. So we try to put one of these FSO links over 19 kilometers, 20 gigabit. Over the last 6 months, 99.6% availability. The product is much more mature, and we have some of the old product. They have a problem, they lose pointing, you have to go and manually readapt them. The Tara product of Google is is really good. So I think the potential is there, but of course at some point you may lose the signal. If you have fog, it is what it is. If you have a cloud, it is there. And often when you have an FSO system, you will have a backup RF system with it. So you will not lose completely connectivity. You will go from 20 gigabit to maybe 500 megabit for the fraction of time where you have this outage. And then from the sky, you have to have site diversity. And here I'm trying to advocate in our part of the world, we have the right kind of weather. We do not have a lot of clouds, and that's why we need calculation with 3 optic gateway stations. In Saudi Arabia, UAE, Qatar, we can have pretty much 99.999% availability. Something that requires 9 optic gateway stations in Europe, and the study has been done by the European Space Agency. So there are solutions to go around this problem.
Deployed in India.
Sorry?
The Google system deployed in India. They're deployed in India.
In India? Oh, the Tara. Yes, of course. Yeah, I know that very well. And also in Africa, between the 2 Congos. And it is a technology that is, finding a market. But mostly we are talking here terrestrial, not the one in Japan. They are for the space. Here we are talking 20-kilometer line of sight, ground to ground. Yes, Professor.
For the ground to air space optics, do you have to worry about eye safety? I wonder also about the tracking and pointing. Like, would you use a radio feedback to maintain the alignment?
Yes, there is. Eye safety is already taken into account when you buy one of these. There is the laser category, so it's already taken into account. And the pointing, acquisition, and tracking. This is the bread and butter of any FSO systems. And in my opinion, what we have with the Tara system is quite advanced, automatic. It works very well. It starts usually any kind of pointing, acquisition, tracking mechanism. Start with some course. Kind of estimation or acquisition of the signal, even for space, using GPS, let's say if you're operating in space, and then you refine, essentially, and you keep tracking that particular signal for maximum reception.
So the feedback will be via radio?
Yes, by radio, that's right. Yes, that's right. Usually in the analysis band, to avoid, because the whole point behind FSO is that operating in the analysis band, so we are not trying to get any frequency latched resources.
Thank you very much.